Hi, Discrete Math. So this is the homework 9 preview video, which I will be going over similar problems that I've assigned for this week's homework. Okay, so let's go over number 6. I think equivalent to number 6 is I assigned number 7. So let's go over this problem asks for the domain and range for each of these functions. So let's think through about A. So A is the function that assigns to each pair of positive integers the first integer of the pair. Okay, so in this case, I think the domain part, it's pretty easy to figure out. The domain is going to be, it's a pair of positive integers. So how we write this, if it's a pair, then we write it's z of this means positive integers. Z generally means this is integer. Okay, so this is a positive integers, and the second of the pair is also going to be the integer. It's also going to be positive. If we're talking about the negative integers, then we write a negative symbol on top. Okay, so this is our domain. Pretty easy to define because we were just told what our domain was, and now we have to find the range. The range is going to be the first integer of the pair. Our first integer was this. So that's just going to become our range, which is the positive of our integer, and we're done with this part A. Alright, so let's go on to part B. The function that assigns each positive integer is its largest decimal digit. Alright, so again, our domain for the second problem is going to be the positive integer. So it's going to be z positive. And the range, this is going to be, we would write this such that as long as x is the positive integer, then our domain is going to be x is less than. It's going to take on that decimal value. This is a pretty fancy way of writing it. You can also write that out by just listing all the numbers. You can include 0. You don't have to include 0, but I'll include it because you can have a 0 as its decimal. 1, 2, and list it all the way out to 9, because if it becomes 10, then it'll take on that decimal value of 0, and which is included here. Okay, so you can either write it this way or just list out all of the possible values of the range. Okay, so C, this was particular to, I guess, those students who are studying computer science. The function that assigns a bit string to the number of 1 minus the number of zeros in the string. So I took this question out for 7, just in case if you're not familiar with computer science, then you might not be able to get to this question. So, but for those of you guys who are familiar with they're talking about, for part C, the domain would be just a set of all strings. A set of all strings. And the range would be, you can think the best, we wouldn't be able to list out. This would be just all integers. So it'll be just z. I should probably tell you guys that if you're not familiar, then this symbol, this is the integers, natural numbers. These are the natural numbers. And also Q with that. These are the quotient numbers. And yeah, if anything more that we're going to use, but we will mainly be using the integers and the natural numbers. And of course, you guys know this is the real numbers. All right, so D, the function that assigns to each positive integer the largest integer not exceeding the square root of an integer. So that's a good problem. So for D, this would be, the domain would be, you can list it out. It could be 1, 2, 3, and it'll continue. Or you guys can just write z with a positive because this is the same thing as positive integers. And the range of this is going to be a set of whole numbers. Okay, so set of whole numbers. Or you can just list it out again. It could be 0, 1, 2, and it'll just continue. Okay. E, I'll just tell you guys, this is again, so I guess part C and E, this is optional, only for computer science students. The domain would be 0, 1, 0, 1, 1, 0, 1, 1, all of those is the binary numbers. And the range would be, it's a string, the longest string of the ones in the string. So the range would be 1, and it could be also 1, 1. The third option would be 1, 1, 1, and so on. Okay, so that was 6, which is very similar to 7. These problems are not hard. You just have to think about the wording of each problems. Let's go on to the next problem I have, which is 16. I assigned 17, which is similar to 16. All right, so let's go over this. Consider the function from the set students in the discrete math class. All right, so it's asking if you guys can apply the definition of one-to-one. Right? It's not really asking about the onto in this case, just one-to-one. So mobile phone number, most of the cases, I assume every student will have their unique phone number. So yes, this is one-to-one. Case B, student ID number. Of course, this would be one-to-one. Every student will have their own unique student ID number. Part C, final grade in class. This is not one-to-one because multiple students can get A's. Also, a lot of students can get the same letter grade. So this will not be one-to-one. For D, this is again also not one-to-one. I'm assuming that more than one student can be from the same same town in the grade. Okay, so just an additional info from the book. This is X and this is Y. One-to-one has to be unique. So if you have A, B, C, D, E, F. Well, even before we talk about the one-to-one and onto concepts, let's check if this is a function. Okay. The definition of a function is that it's kind of like when I think you guys have seen the image of a slot machine when you were first introduced to function. So in that sense, what it is, how to tell if a function is or not, you have to make sure what your input is. You have to know what your output is going to be. So let's say this is our case. All right, so if I put the A into the slot machine, I'll get a value of D out. Also looking at this chart, if I put B, I'll get E out. Same thing, if I put C, I'll get an E out. So that, because we are sure what to put in and what output I'll be getting out, this is a function. The example of something not being a function is something like this. Let's say A is E, and B gets me E, and C gets me F, or it could also get me E. So let's say something has been mapped like this. If I put A inside of the slot machine, I will be getting out D as a result. If I put B in, I will be getting out E. So far, so good. So far, it's a function. But here is where the problem arises. If I put C, then I could be either getting E or F. So this is the definition against function. So this is the case where this mapping would not be a function. Okay, so for this chapter, we will be assuming that we are working with the function mapping. So this is a typical case of one-to-one. Every student, in this case, which is X, student A, B, and C, are assigned a very specific value, D, E, F. It could be, for our case 1, would be our phone numbers, and for case 2, it was our student ID numbers. Okay. What if we had a 4th student, student D, and that student received a grade of F? Okay, so let's say student A receives a grade of D, student B received a grade of E, and there are 2 students who received a grade of F. This is a function because we know what our, given our input, we know exactly what our output is. But this is an example of a function that is not one-to-one. Okay. All right, so let's go on to the last example of this chapter, which is 22. I assigned 23, which is similar to 22, so let's go over these questions. So we have to determine whether these functions is the bijection. So bijection is a word that satisfies both one-to-one and onto. So for these problems, we're going to have to test if given problem is an onto as well as one-to-one. All right, so let's do that. So for A, f of x equals to -3 plus 4. So we kind of immediately know from using our algebra background that this is going to be one-to-one and onto, but how do we mathematically rigorously prove that? So to proving one-to-one, we have to need to show that for every value that we put in x, there will exist a unique value of y. Okay? So this would be our general rule. To prove one-to-one, we need to show that for some value x, and we can even go and say x is in R, and also y is in R, because we're mapping from R to R. All right, so what's f of x? F of x is -3x plus 4, and we have to prove that there will be a unique value of y. So f of y is going to be -3y plus 4. Subtract 4 both sides, divide both sides by -3. We get x equals 2y. So therefore, we have just shown that this function is one-to-one. If you get something like maybe like this, then you have proved that this function is not one-to-one. So this is our goal. Our goal is if we set these 2 functions, and if we do get to a value of x equals to y, then we have proved one-to-one. And we'll see a case where this is not satisfied. All right, our second step is we need to prove that this is also onto. So onto, we are trying to prove for every y in R, there exists x in R such that f of x equals to y. So this is what we're trying to prove. Okay, so let's check. This is actually a really fancy word of saying, does the inverse exist? Okay, so if we go back to our algebra class back in high school, we were told to find the inverse. How do we do that? We first set this as y. So y equals to -3x plus 4. We'll get the inverse as x minus 4 over -3. So our inverse statement exists, which means if I were to plug this in to our x, we should get the value of x. So therefore, this function is also onto. So this would be, function A would be a bijection.